actually giving this talk, it should really be Graham Markle. We just have a clash of concept conferences. It's also the RISC-V Summit, and the way things fell, he's actually out at the RISC-V Summit, where he's actually talking about my work, and I'm here talking about his work. It all made sense at the time. So I'm going to talk to you about compilers and why they're a good thing. And if we want to develop IoT software securely, we've heard we need good software engineering practices. As programmers, we need good coding guidelines, and you can have the Cert C or you can have MISRA, and there are plenty of others out there. There's the human factor. You actually need the engineering teams to follow the process, and that is about education and training. But even the best professional programmers are improved by having tools that help them to follow that process. And this talk is about one tool that can help them follow the process. So why the compiler? Well, we all know security is a system-wide problem. And which is the one tool that pretty much looks at all your code? Answer, the compiler. Now, if it's C, C++, it's obviously compiled. Java is still looked at by a compiler to turn it into bytecode. Assembler goes through an assembler that's bolted into the C preprocessor and forms part of the compiler, so it's all part of the same tool chain. And the only way you possibly get that is if you've got some wacky hardware that can interpret a scripting language directly, not terribly common, or if you're back in the 1960s and 50s and putting raw hex binary machine code in. So those two aren't terribly common. So an obvious thing is to get the compiler to see if it can help. It's well positioned to help with security. And it can help in two ways. It can warn of bad practice. You've done something when I compile your program, this doesn't look like a good idea. Go and check if it's right. And probably more usefully, it can help with the heavy lifting. There are all sorts of security techniques that are well known, are mind-numbingly tedious to implement and really hard to get right. And the compiler can add features to make that easier for you. And this is not a magic bullet. We're not magic, here's a compiler, it'll magically make your code secure. It's saying you're a professional security programmer, will make you more productive, more consistent, higher quality. Now, to make this all happen, we were funded by Innovate UK. It's a single company project, it's one of their small projects, so it was just us, but we did have some help from academic talks I'll talk about later. And the goal was not to invent something new. These techniques are all well known. It was to take those techniques and try to get them into mainstream compilers. We're an open source company, we develop open source compilers, so we did this for GCC and LLVM. And all the work's open, help yourself. So the context of this is firstly the academic context. So we worked with Elizabeth Oswald and Dan Page and the Leakage Aware Design Automation project at Bristol University. And both Elizabeth and Dan were consultants to the project, and we reviewed the progress with them every 3 months. And secondly, we have track in this field. In the compiler space, you can go and look at the video. There's the electronic version of these slides will have the soft link in there of my colleague Simon Cook talking about how you develop LLVM to run on a processor which has built-in control flow integrity. A processor where what an instruction means depends on what the previous instruction was it executed, so you can't change the flow. And reverse engineering that in the compiler so you generate the right magic bit strings turns out to be hard. So we've got track record in that space. So what did we do? This is the only bullet point slide, I think, in the pack. I haven't got time in this talk to go through all this. The sort of things we looked at, and the first one I'm going to talk about in more detail, the stack and register arrays. I call a function and I return from it. And I tend to leave stuff on the stack, which can then be hoovered up by someone malicious. Bit slicing. That's typically used in block ciphers, where instead of doing everything a row at a time, you do it a bit at a time, all the rows at once. That's done for efficiency purposes. It turns out to be actually cryptographically quite a good thing to do in terms of information leakage. It also is very tricky to do by hand. And so we've done a bit of work on automating that. Control flow balancing. So you shouldn't really have sensitive variables causing your control flow to go in two different ways. But if it does happen, at least balance the load so it takes the same time, the same energy, all the other same profiles going down each side. Sensitive control flow. Well, before that, that should have come first, which is if you mark a variable as sensitive, it's a cryptographic key, then we can flag up and say you've used a key to control a loop or to control a flow. And that's very similar to standard static analysis you get in modern compilers, and it is equally complex. We did a lot of work on that, and we haven't actually got anything really good to show for that. It was a research project. That's one. Yes, we can see how it could be done, but we couldn't do it in this sort of scale. Bit splitting, that's the idea. If you must keep something in memory, don't put a 32-bit value in one place where someone can scan through the memory and find it. Put a bit here, a bit there, a bit over there. And then every time you use it, combine the bits, do your computation, put the bits back out again. No one ever does that by hand. It's just too mind-numbingly tedious. It hammers your performance out of sight, but you're presumably not doing much of this, and performance is not a factor. It's security is a factor. And defensive stores. So one of the ways you protect against someone shining a bright laser on your smart card to knock electrons out of your program and change the flow of control is you assign a variable. You say x equals some value. And then a bit later you say, if x hasn't got that some value, assign it again. So if I knock out 1, I'll get it the second time. And a modern optimizing compiler says, that second store is redundant, I'll throw it away. Which is why a lot of security code is compiled unoptimized, which is stupid. Not only can we turn the compiler off so it doesn't do that, why don't we do it for you? Mark this as a variable to be defended, and every time you assign it, we'll put another one as far away as it can be in the basic block before it's used, and we'll do that duplicate for you. And then you can get it right every time automatically. So those are the things we've looked at. Let's look at stack and register arrays a bit more detail. And this is covered, for example, in the Cert C Mem 03 clause. Clear sensitive information stored in reusable resources. And of course, the stack is a reusable resource. And there are proactive things. There are explicit B0s, as memset S. Various operating systems provide you with things. And if you use Ada, then Ada, thanks to Rod Chapman, has finalizers, limited private types that you can use to clear stuff away. But the problem is that stack, which is ephemeral storage, you don't explicitly say, here's some stack, you just have variables and they're on the stack. And apart from the Ada approach, you haven't got an easy way to address the stack and say, clear it and explicitly do it. The problem is, all of these things are explicit. I've got to remember to clear stuff. Wouldn't it be nice to automate it? So let's have a look at a little program. So here's a program. It's a trivial program. It's a main program which you give it an argument, which is a secret, and then you mangle it by swapping the bits around and return the mangled value. And the problem is, if I give it this number, which happens to be dead beef, okay, and I return the mangled version feedback, the problem is dead beef is still left lying on the stack when I return to main and can be accessed. And indeed, if I've got a variable in main and I happen to know the shape of my stack on my processor, I can indirect and read that value off. So that's how some exploits work, is by finding stuff lying around on the stack. Now, what we do is we change it. We add a new attribute. So attributes are a standard part of C++, and they get added to C anyway. So we give it an attribute called erase stack. And what that does is, when the code is compiled, as part of the epilogue of the program, where the function returns, it has a little loop just to clear out the stack. It knows how big the stack is, it wipes it all away. So that when I'm back in main, everything is 0 there. Okay? And that's all it is. And it's actually not terribly difficult to implement. And you can do variants of it. You can have a flag to the compiler where you say, make all functions have erase stack. Okay, so you can do it. And there's a penalty, there's a performance penalty, because you've got to wipe the stack each time. And if you use things like long jump and set jump, there are also niceties of getting rid of all the stack frames in between your long jump and set jump. But now I'm programming in C, and I have a fairly consistent way of making sure nothing's left on the stack. And I can do the same with the registers. I can have erase register, which throws all the, make sure all the registers are zeroed. So that is just a quick overview of one of the techniques. That code's available on our Git repositories. We're trying to get it upstream into GCC and LLVM, so it's grinding through the community approval process. I now, rather than trying to do a live demo, have a video of Graham Markle and a very clever work experience student demonstrating the technology.
Okay, so Graham and I have built this logbox application which stores an 8-digit code on the stack and then prints it to the screen when we lock it. You can see it's locked and we've printed the code to the screen. I've also made this exploit script which, if we type in DD, will just interact with the -1 over serial. We can also send it the correct code,
which is 6559
6559
FF7B.
FF7B. And you can see that's unlocked it. So to relock the device, reboot it, and lock it again. If we now type exploit, you can see that we've managed to successfully exploit the vulnerability in the code and get the secret, which is 39C549. If we now start to relock again, we can wait for a bit. The only line's changed. We're going to change to make the program secure is we're going to add this stack arrays attribute to the print number function. All this means is the print number function is the one which puts it on the LCD screen, and because we've passed the secret to this function, it's on this function's dead stack frame, and that's what we're doing when we're exploiting. We're reading past that and printing it out back. So what the stack arrays attribute does is it'll tell the compiler to overwrite this area with zeros in memory, thus protecting the secret. If we now flash the secure version to the box and lock the box again, we try and exploit it again, we can see it doesn't work and the secret isn't there.
Okay, a loop. Help, how do I get rid of that? So, that's it. It's worked. It's easy enough that a bright sixth former in a week with good mentoring, the voice in the background was Graham, can actually write a program and an exploit and demonstrate how by turning on a stack erase when compiling the code makes the exploit not unable to find the key lying on the stack. So the takeaways are threefold. Developing secure IT software requires good practice. We all know that. Good practice is supported by good tooling, which is what this session is about. And lastly, the compiler is a great place for security tooling. And there's lots of time for questions. Thank you.